that we know how the NDB and ADF work, how is the information presented to the pilot? It depends upon the degree of sophistication of the indicator. There are three types: the relative bearing indicator, RBI, the moving card, RBI, and the radio magnetic indicator, RMI. The most basic instrument is the RBI, which has the points of the compass presented around the dial, with 0 or 360 degrees at the top. This is not a heading indicator, and it does not state in which direction the aircraft is flying. Simply that the aircraft nose is at 360 degrees, and the NDB is in the direction of the needle. So, if an aircraft was flying a heading of 060, then turned to fly 090, the numbers around the dial will not turn. They are fixed, but the needle will drop to 240 on the RBI. On the direction indicator, the dial will turn from 6 to 9, but the needle will not move. It still points at 12 o'clock. What then does the RBI do? It simply points its needle at the NDB and shows this position in relation to the nose of the aircraft on an imaginary compass. Rather than a compass, the face of a clock could have been used. So an RBI bearing of 270 degrees will be a bearing of 9 o'clock. The weakness of the RBI is that the pilot has to make a calculation to find what magnetic heading to fly to the NDB. You have to know how to do these simple calculations. Here, we see that the RBI indicates that the NDB to which the aircraft is tuned has a relative bearing of 270 degrees that is relative to the aircraft's nose. The direction indicator is showing a heading of 060 degrees. To calculate the magnetic heading, the QDM to the NDB, draw a picture with the information from these two dials. Add the relative bearing, in this case 270 degrees, to the heading of 60 degrees. This makes a total of 330 degrees. If the total of the heading and the relative bearing comes to more than 360 degrees, deduct 360 from your total to give the magnetic heading to the NDB. For example, a relative bearing of 270 degrees and a heading of 180 degrees totals 450 degrees. Take away 360, which leaves 090 degrees as the magnetic course to steer to the beacon. Some RBIs have a movable card, which allows the pilot to turn the card to show the aircraft heading at the top of the dial instead of the 0, which always appears on the fixed card RBI. So in our example, the pilot can put 60 degrees at the top of the dial to match the direction indicator. The ADF needle on both RBIs points in the same direction to the NDB. The number on the basic RBI shows 270. But now, the number on the RBI with the movable card, to which the needle is pointing, is 330 degrees. The number 330 reflects the heading of 060, plus the relative bearing of 270. In other words, this is the magnetic track, the QDM, to fly to the NDB. The weakness of this system is that the pilot has to manually turn the card on the RBI every time his heading changes. If our pilot turns from 060 to 090 degrees, we see that the beacon now has a relative bearing of 240 degrees to the nose of the aircraft. The NDB is in the same place. It is just the aircraft's heading that has changed. So if we add the heading of 090 degrees to the relative bearing of 240 degrees, we have the same magnetic bearing to the NDB of 330 degrees. With a movable card set at 090, this calculation is done for the pilot, showing that the NDB is on a magnetic heading of 330 degrees. This manual adjustment is avoided in the RMI, the radio magnetic indicator, which incorporates a moving dial which shows the aircraft's magnetic heading. The RMI then interprets both the radio input from the beacon and a magnetic input to provide continuous magnetic heading and beacon bearing information. The RMI is much easier to interpret. Sometimes it can have two needles, tuned to 2 NDBs, or 1 NDB and 1 VOR. If it is tuned to 1 NDB and 1 VOR, the NDB is the wider needle. Electronic displays are now frequently used, and it is the RMI information which is displayed, but with the additional features of a deviation bar. This represents the track you want to fly on, and it shows how many degrees you are away from this. When the bar is in the centre, you are on track. We have looked so far at obtaining the magnetic bearing to an NDB, but sometimes it is necessary to determine a true bearing to an NDB. To convert a magnetic heading to a true heading, one must deduct a west variation and add an east variation. Another calculation, known as deviation, may be necessary if you are given a compass heading. A compass heading is an error in the magnetic compass due to the magnetic effect of the metal of the aircraft. A compass card located next to the compass states what this error is on different headings. To obtain a correct magnetic heading, deduct a deviation west and add a deviation east. Then proceed to convert the magnetic heading into a true heading. Let's go over one more example to find the true bearing of the aircraft from the beacon. The heading is 090 degrees compass. Deviation is 12 degrees east. So heading is 102 degrees magnetic. If variation is 15 degrees west, true heading is less by 15 degrees. Namely 087 degrees true. That completes the preliminaries. The heading is 087 degrees true. The NDB is given as 075 degrees relative. So the NDB true bearing is 087 plus 075 degrees, which is 162 degrees. The reciprocal of a heading means going in the opposite direction, so add 180 degrees to the heading. The aircraft therefore has a reciprocal bearing from the beacon of 162 plus 180 degrees, 342 degrees true. Now that we have seen how the NDB operates, what can it be used for? Homing to NDB, tracking to the NDB, intercepting tracks to an NDB, procedure turns as part of an approach procedure, holding patterns. We'll look at each in turn, starting with homing. This is a procedure whereby a pilot flies towards an NDB by keeping the head of the ADF needle at the top of the display, in the 12 o'clock position. If there is no wind, the pilot will fly in a straight line to the NDB. But if there is any wind, the aircraft will drift, and the pilot will need to constantly change his heading in order to keep the needle at 12 o'clock. It is poor airmanship to fly like this. Consequently, the correct way to fly to an NDB is to follow a defined track. This is tracking and requires the pilot to compensate for any drift caused by a crosswind. Here, we see the pilot regaining track after being blown off track, then making a 10-degree allowance for wind. Notice how the relative bearing of the NDB has changed from 000 to 330 to 350 degrees. Tracking away from an NDB is the same procedure, except that now, if the NDB is directly behind you, it is 180 degrees from the aircraft's nose. If the relative bearing is more than 180 degrees on your ADF, the NDB is to your left. Here we see an aircraft maintaining a track of 100 degrees. The starboard drift of 23 degrees is known, resulting in a heading into wind of 077 degrees. The relative bearing is 203 degrees, so the NDB is to the left of your tail. If the relative bearing is less than 180 degrees, the NDB is to your right. Here we see that port drift is anticipated, resulting in a heading into wind of 110 degrees. The relative bearing is 170 degrees, so the NDB is to the right of your tail. Next, we look at intercepting a nominated track to an NDB. Perhaps it is part of an arrival procedure. Let's say the NDB is ahead and on your left, and you are to track to the NDB on a QDM of 270 degrees magnetic. Remember that these radials are like spokes of a wheel and move out from the centre. So, if you are flying to the beacon, your heading is that of the radial leaving the beacon, which is the other side of the beacon to where you are at present. Do not consider yourself to be on the 090 radial, the reciprocal of 270, because you are not flying in the direction of that radial from the beacon. If the aircraft has an RMI, your heading is displayed at the top, and the ADF needle points at the NDB, showing the magnetic heading to fly to it. At the start of this sequence, we see that in relation to the aircraft's nose, the NDB is just slightly to the left, so at a relative bearing of about 325 degrees, which is not shown on the RMI. But the magnetic heading is shown at 295 degrees, which is the heading to fly from where you are now to the NDB. As you continue your heading of 330 degrees, the relative bearing to the NDB decreases, and the needle falls in the 6 o'clock direction. When the needle points to 270 degrees, you are on the 270 degrees magnetic radial of the NDB. If the aircraft only has an RBI and no movable card, some mental arithmetic is required. The problem is that the basic RBI does not tell you when you have reached the designated radial and you need to turn. It just gives you a relative bearing to the nose of the aircraft. But a simple calculation achieves this. Remember that relative bearing means the angle between the nose of the aircraft and the beacon. So subtract the designated radial from your heading. If the answer is positive, turn left when the needle points to that number of degrees from the top of the dial. If the answer is negative, turn right when the needle points to that number of degrees from the top of the dial. Let's use some figures to illustrate this. Your heading is 330 degrees, and you are to intercept a radial of 270 degrees. Deduct 270 from 330, which is plus 60. Turn left when the needle is 60 degrees left of the top. If your heading now is 045 degrees, and you are to intercept the 090 degrees radial, deduct 090 from 045, which gives minus 45. So turn right when the needle is 45 degrees from the top of the dial. A procedure turn describes a formal pattern for flying an approach to an airfield based upon the location of an NDB on or near the airfield. There are two main types of procedure turn. In the first, a time or distance to fly away from the NDB is specified. Then a turn of 45 degrees is made away from that radial, followed by another turn of 180 degrees back to intercept the inbound radial of the NDB. The second type starts in the same way, with a timed or distance outbound leg. This is followed by an 80-degree turn and then a 260-degree turn to intercept the inbound radial. In VMC, you can check visually where you are as you approach the airfield for the first time at the start of the procedure. But in IMC, the NDB enables you to find the airfield from any direction and then start the procedure turn. The procedure has to be started within 30 degrees either side of the procedure radial. Let's look at the approach chart for Oxford, runway 19. Central to the procedure is the OX. A small aircraft tracks outbound on a heading of 001 degrees from the beacon, which means that the ADF needlehead, which always points to the beacon, is on the reciprocal of 001 degrees, which is 181 degrees, behind you. If you are in a Category 3 aircraft, a jet, you are told to track outbound on 354 degrees, which means that the head of the needle points to the reciprocal, which is 174 degrees. After 6.5 nautical miles, you start to turn right, until you intercept the 194 degrees track to the runway. How do you know when you are on this NDB radial? A heading of 194 degrees on the DI is not enough to tell you this, as you could be on a heading of 194 degrees to anywhere. You must also intercept the 194 degrees radial on the NDB, which means that the DI must be set to 194 degrees, and the NDB needle is pointing to 360 or dead ahead. Remember that the head of the NDB needle represents its position in relation to the nose of the aircraft. If you maintain 194 degrees on the DI, but the head of the NDB needle is to the left of centre, you are still flying on a heading of 194 degrees, but you are being blown off course to the right. If your track is good, you then follow the descent pattern, which is shown on the approach plate. The last use of the NDB is for holding patterns. Busy airports will frequently require approaching aircraft to delay their approach and fly round and round in a racetrack pattern over a fixed point, marked either by an NDB or a VOR, until they are allowed to approach the airfield. During the hold, turns are to be carried out at rate 1, and the outbound and inbound legs will normally be 1 minute in duration at and below 14,000 feet, and 1.5 minutes in duration above 14,000 feet. Aircraft will inevitably approach the NDB from different directions, and they have to follow one of 3 different joining instructions. Those aircraft approaching from Sector 1 follow what is called a parallel entry. Those aircraft approaching from Sector 2 perform an offset entry procedure. Aircraft from Sector 3 approach the beacon directly. Aircraft enter the hold at a given altitude and stay there or stack until they are allowed to descend to the next level, 1,000 feet lower, and ultimately leave the hold to approach the airport. We have already seen in the lesson on propagation that several factors affect the accuracy of radio waves, including NDB transmissions. Here we will just summarize these factors, starting with static interference, caused by either thunderstorms or precipitation. When water droplets or ice crystals collide with the aircraft, there is a reduction in the signal-noise ratio and a consequent wandering of the RBI or RMI needle. The audio signal will have a background hiss, which is also likely to be present on VHF frequencies. Thunderstorms produce large electrical discharges across the electromagnetic spectrum, including long wave and medium wave. The effect on the ADF is to make the needle point to the offending cumulonimbus cloud or clouds, so that the instrument is completely unreliable. Night effect is caused by the interaction of surface waves from the NDB with sky waves from the same NDB. During the day, the D layer of the ionosphere attenuates all long and medium waves, so that ground waves are the only means of transmission for NDBs. At night, the D layer becomes deionized, and sky waves may be emitted from an NDB, which are received out of phase with the ground waves. The effect is most pronounced at dawn and dusk, as the ionosphere is changing both in intensity and height. The ADF needle may wander, and the audio may fade as the two signals drift in and out of phase with each other. Station interference occurs when two NDB signals overlap. To avoid this, station locations and frequencies are carefully chosen to ensure a daytime level of bearing accuracy, known as the Designated Operational Coverage, DOC. However, at night, NDBs far away may produce interfering sky waves. Coastal refraction, caused by radio waves travelling faster over sea than land, results in radio waves which cross the coast at angles other than 90 degrees, the normal, bending away from the normal as they cross from land to sea. The greater the angle of the point of crossing from 90 degrees, the greater the error. Mountains can cause reflections and diffraction of radio waves. The solution is to fly higher. Quadrantal error is caused by the airframe, which distorts the incoming radio signal. It is so called because the distortion is worst in the quadrants, that is, at 045 degrees, 135 degrees, 225 degrees, and 315 degrees. The error mostly affects older aircraft, as newer equipment resolves this problem by means of an electronic device. Stray metal objects or a live mobile phone near any instruments may cause interference and an inaccurate reading. Dip error refers to an inaccurate ADF reading when the aircraft is banking. Because the system is designed to work in horizontal flight, any banking will tilt the horizontal arms of the loop antenna, and this produces an electrical current which causes a small error in the indicated bearing. If a left wing is lowered, the ADF needle will fall in the same direction by about 10 degrees. Finally, in the list of errors, there is the cone of silence, extending upwards from the beacon. Within this cone, accuracy is poor. It should be noted that most ADF equipment does not include a failure warning indication of either the NDB or the ADF. Pilots should continuously monitor the bearing and the identification signal, especially during an approach using an NDB as the primary source of navigation. We have also seen in the lesson on propagation that various factors affect the range of a radio signal, namely transmitter power, the frequency, the surface, type of transmission, precipitation, and receiver quality. As the range of the aircraft from the NDB increases, so the signal becomes weaker, and therefore the signal-to-noise ratio decreases. In the United Kingdom, the minimum signal-to-noise ratio which is considered acceptable is 3:1. This should produce a bearing accuracy of within plus or minus 5 degrees by day, only within the designated operational coverage. This brings us to an end of the 2 lessons on the NDB and the ADF. In the first lesson, we looked at the principle of the loop antenna and the position of the 2 null readings, and how this ambiguity is resolved with the sense antenna. We considered the operation of the goniometer, which has replaced the moving loop antenna, and we have looked at the emission characteristics of NDB transmissions. In the second lesson, we looked at how to interpret the ADF instrument in the cockpit, how to fly to and from, how to intercept an NDB radial, and how to fly various NDB procedures. We also looked at the factors which affect the accuracy and range of an NDB.